Hello there, this is Jude Socrates. Welcome to video number 15 in my series for multivariable calculus, known as Math 5C at Pasadena City College. So in our last video, we were able to set up and compute a double integral in polar coordinates, where I believe our domain was an annulus, so it was a disk where we removed a disk from within. So today we are going to continue with double integrals over polar coordinates, but this time we're going to use them to first find the volume of solid, which is best expressed in polar coordinates, shall we say. And then we're going to look at double integrals over generalized polar regions. So in the same way that we talked about type 1 and type 2 double integrals when we were doing dx dy or dy dx, we're going to also see double integrals where the inner integral is no longer bounded by constants. So that inner integral is usually the variable dr, or the variable r, I should say, I guess. And the lower or upper limit of r is no longer a constant, but rather a function which depends on theta. So we're going to see that a little bit later. So for our first item on the agenda, we are going to solve this problem. We will find the exact volume of the solid bounded above by the circular paraboloid z equals 25 minus x squared minus y squared, and bounded below by the xy plane. Okay, so this is an upside down paraboloid, and we have the bottom will be just the xy plane. Let's go to GeoGebra and draw ourselves a nice diagram. All right, here we go. So we have z is equal to 25 minus x squared minus y squared. All right, ooh, nice red. So there's our paraboloid, and we have the xy plane. Okay, so we have to interpret the solid as a double integral. Okay, so of course we're finding a solid, so we'll have to imagine little boxes inside our paraboloid. Okay, very narrow base, delta x, delta y, and then the height is controlled by this paraboloid. So we know its equation. We know the height, that's just the z value. Okay. What is just as important is the domain, and I think if you look from above, we can easily see that the domain that we want is a circle. Okay, so or rather a disk. So we know, of course, from our first video on polar coordinates that a disk can be interpreted as a polar rectangle. Okay, so we need the disk centered at the origin, radius 5. All right, so now that we know our domain, we can set up our double integral. All right, so here is our double integral template in polar coordinates. So our theta is on the outside, r on the inside. Don't forget the extra r, right? So we have a full disk. So theta is going from 0 to 2 pi. And then the radius is 5. So r is going from 0 to 5. There you go, 5. All right, so we said that the height is controlled by the z value. So that's 25 minus x squared minus y squared. So of course, we can think of that as 25 minus r squared. Okay, so remember that x squared plus y squared is r squared. All right, so it's not a particularly difficult integral. Notice that there is no theta within our problem, within our integral. Okay, and the r values here are constants. Okay, so we have something which is factorable essentially. Remember how when we had dx and dy, if your function factors as p of x times q of y, you can separate the integral for dx with the integral from dy. Okay, so we can essentially do the same thing over here. So we can write this as a product. We have d theta And of course, think of it as a function of just constant 1. Okay, and then we will multiply to the second integral involving r. Okay, so of course, both integrals are fairly easy to compute. Right? So the first one is just theta going from 0 to 2 pi. So that is simply 2 pi. But the second one, we do have to integrate. So first we distribute the r. So we have 25r minus r cubed. And then we take the antiderivative. Okay. So that will give us 25r squared over 2. So let's make a fraction. 25 over 2r squared. And then minus r cubed becomes r cubed over 4. Okay, so 1/4 r to the 4th power. And our limits are from 0 to 5. Okay, so we'll go from r equals 0 to r equals 5. Maybe I can make it look nicer here. Yeah. There we go. R equals 5. And this is r equals 0. Now, that looks a little bit nicer. So, of course, at 0, everything goes away. So, we only have to worry about 5. So, we get another 25 there. Let's write it as 5 squared. And then we have 5 to the 4th power. Okay, excellent. And we can now erase these. And notice I left it factored because there's a 5 to the 4th hiding there and hiding there. Okay, so that can all factor out. And we will get 2 pi times 25 times 5 to the 4th power. So we're going to take that away. And that goes away. That goes away. It's all accounting. 1/2 minus 1/4. Yeah, that just simplifies to 1/4. Okay, so there we go. We have 2 pi. Okay, we can cancel a 2 with a 4. So we get as our final answer, let's just write it over here. I believe we're going to get pi over 2. And then we multiply by 5 to the 4th. So 25, 125, 625. 625 pi over 2. What's that approximately? About 981. Yeah. So yeah, it's a very tall portion of the paraboloid. So it's no big surprise that the volume is not exactly small. All right, so let's now continue on page 33 of our PDF. And this is where we're going to learn a little something about general polar domains and how to set up integrals, double integrals over general polar domains. So first of all, how do you recognize that you're dealing with the general polar domain? Okay, so remember how we did type 1, type 2 scans, all right? Shoot vertical arrows for the type 1 scan, shoot horizontal arrows for the type 2 scan. For a polar domain, the arrows come from the origin. Okay, so let me scroll up a little bit here. Okay, so start at the pole and pretend that you're throwing arrows. Okay, you're shooting arrows. Okay, you're an archer and you're kind of standing there and spraying that region with arrows. And notice that we enter the region at some angle, theta equals alpha. And then when we keep going, the arrows enter the region at one polar curve. So we can call that r equals g1 of theta. And they all exit at another polar curve. We can call that r equals g2 of theta. Okay? And the last arrow gets shot from this angle, theta equals beta. Okay? So you can probably start putting that all together. The outer integral will be theta goes from alpha to beta. Sounds familiar, same as before. But now R is not going from A to B. Okay, so R is going from G1 of theta to G2 of theta. All right, so we're going to keep working on that paraboloid that we did a minute ago, but I wanted to show you this example from our PDF. Okay, it's related to what we're looking at, except we have 5 minus x squared over 5 minus y squared over 5. So that has the advantage of a more rounded shape. Okay, ours was really tall and really narrow. This one is a little bit more spread out, more evenly spread out. Okay, but I wanted to show you this because in this example, we're looking for the portion which is to the right of x equal to 3. Okay, so in the previous example related to this, we found the volume of this entire parabolic portion, but now we're cutting off a little slice. Okay, it kind of looks like cake, and we're cutting off the edge for ourselves. Yeah. Okay, so why is this good for a polar region? So first of all, symmetry. Okay, so notice, of course, that the upper portion and the lower portion are exactly the same. Okay, so just like in basic calculus, when that happens, you can take half of the solid, half of the area, and just multiply by 2. Okay, so when we scan our domain using arrows, we start at alpha equals 0, and then the arrows enter the vertical line first, and then we'll exit at the circle. Okay, same pattern until we reach the last arrow, and that is where we have some angle. Okay, so how do we find that angle? Use a little trick. Okay, so the radius of the circle is 5, just like ours. Okay, but since we have x equals 3 over here, solve the system of equations when x is 3 and x squared plus y squared is 25, because we also want to be on the circle, then you'll get 9 there. Y squared equals 16, so y will be 4. Okay, you can almost cheat and read it from the graph over here. So there are at least 3 ways to write down this angle. You can write it as inverse tangent of 4 over 3, for example. Okay, and that's probably the easiest way to do it, okay, given the integration that you'll see later. Okay, so what we're going to do is we are going to stick to our last example, but instead of slicing it with x equals 3, we're going to slice it with y equals 4. Okay, so you can probably anticipate already what's going to happen in that case. All right, there we go. Just a little bit of cut and paste. So same beginning, bounded below by the xy plane, but we want to be above y equals 5. All right, so let's go back to GeoGebra and see what it looks like. All right, so there's our solid. We can just type in y equals 5. There's our slice. Okay, so we want the portion of our paraboloid, which is, oh, I'm sorry, y equals 4. There isn't much to slice there. Y equals 4. There we go. So now we can see that there's a little bit of that paraboloid being sliced over there. Okay, so what do we have to do? All right, so look at the domain. So again, look at the footprint over here, and we see the circle that we saw earlier. Okay, and that is now at y equals 4. So of course we get x equals 3. Okay, same circle. So when y equals 4, x squared has to be 9, so x has to be 3, or negative 3. Okay, and again, there's symmetry. All right, so the right half is symmetric to the left half, so we can just start at this angle, and it's the same angle as before. So that's inverse tangent of 4/3. And then we can go up to the middle, and that angle, of course, going straight up, that is pi over 2. Okay, so what about the arrows? Okay, so from the pole, shoot the arrows And you will now enter, let's zoom in a little bit. Okay, there you go. We don't need to see, there we go. So we are going to shoot arrows this way. We are entering the region at the horizontal line, y equals 3, and we're exiting on the circle where r equals 5. Okay, the usual circle of radius 5, that's just r equals 5. Okay, and of course the function that we are integrating is exactly the same. Okay, this is still z equals 25 minus x squared minus y squared, but the domain is a lot smaller. All right, so let's write down that observation that we had. When we scan the region with arrows from the origin, they enter the region at y equals 4, not 5, y equals 4, and exit at x squared plus y squared equals 25. Okay. You know what? My apologies. So basically in our first example, it was pretty obvious that the radius is 5, but that's because we are intersecting the paraboloid with the xy plane where y equals 0. So I'm sorry, where z equals 0. So when z is 0, we get x squared plus y squared equals 25. Okay, kind of skipped over that little detail earlier. Okay, so we already said that this circle is also known as r equals 5. Okay, so that is the upper limit of our inner integral for dr with respect to dr. Okay, the lower limit is this horizontal line, but we need to convert it into polar coordinates. Okay, so for y equals 4, we must convert to polar. Okay, so y we know is r sine theta. So r sine theta is equal to 4, or we can write that as r equals 4 over sine, also known as 4 cosecant theta. Okay, so as you can imagine, in the example in the text, we have secant theta instead. Okay, so slight change in the antiderivative formulas and the trig identities that we are going to require. All right, so let's also write down what we do for theta. So the initial angle is at alpha equals tangent inverse 4/3. That was where our arrows started to hit the region, and the terminal angle is beta equals pi over 2. Okay, so those are the limits of our outer integral magic. So theta will go from, let's just keep it as alpha. You don't want to keep writing tangent inverse out the 4/3 every time you write the next step. So final angle is pi over 2. R is going from, so our lower limit is 4 cosecant theta, and our upper limit is 5. Okay, so we have the same height that we said before is 25 minus r squared. Okay, so that's our setup. That is the volume that we are going to compute. Okay, how about this? Why don't you pause the video and see how far you can go there. You're going to see cosecants, of course, powers of cosecant. And do you remember the antiderivative of cosecant squared? But you might see a higher power. So yeah, try to go as far as you can and see if you can even complete the integral. I would be very impressed if you did. Okay, I'll see you in a second. Maybe I should have warned you that unlike before, where we separated the theta from the r, you can't do that anymore, okay? Because the r portion depends on theta, Okay, so try again. Okay, so here are the next first few steps. Okay, so distribute the r. You have 25r minus r cubed, just like before. Okay, but this time keep it inside the theta integral, because when we take the antiderivative, 25r squared over 2, and then you have r to the 4 over 4 minus, we are going to plug in the lower limit and the upper limit, and there's a theta in there. Okay, so this is no longer a constant that you can take out. Part of it is a constant. Okay, so for 5, we get 25 times 25 over 2, 5 squared, minus 5 to the 4th over 4. And then for the bottom, we will get minus 25 over 2 square, so 16 cosecant squared. This will turn to a plus 1/4 r to the 4th, so 4 to the 4, 16, 64 to 56, cosecant to the power 4. Okay, so simplify, keep going. All right, so we know how to integrate cosecant squared, or we should, but you might have had a little trouble with cosecant to the 4th power. Okay, so here's what you can do there. Break it up. We can think of it as cosecant squared times another cosecant squared. Okay, now we have to remember our trig identities. Okay, so always start with, or at least I do, cosine squared plus sine squared equals 1. Okay, so if you want to see cosecant squared, divide both sides by sine squared. Okay, so 1 over sine squared, that's your cosecant squared. Sine squared over sine squared, that's 1. Cosine squared over sine squared, that's cotangent squared. So we get cotangent squared theta plus 1. And then the whole thing we multiply to cosecant squared. Okay, so 1 plus cotangent squared is your first cosecant squared. Okay, and then we distribute this because we will get cotangent squared times cosecant squared, and then we will have just plus cosecant squared by itself. Okay, and that can join the other cosecant squared over here. Okay, so you can maybe pause the video again and see if you can continue from there. Okay, so I think we can finish this now. We have 64 cosecant to the 4th power, which we wrote out this way. So when we distribute the 64, we will have 64 cotangent squared cosecant squared, and then plus 64 cosecant squared by itself. All right, so that plus 64 can join the minus 200 to minus 136. Yeah, plus 64. Yeah, that's 200. Okay, and then we have this. Now, the derivative of cotangent is negative cosecant squared. So therefore, the antiderivative of cosecant squared is negative cotangent. Okay, so we are now ready to do the antiderivative. So let me put my eval there. We will have 625 over 4 theta. And then that's going to turn into plus 136 cotangent theta. Okay? And then the last term, now you have to do a little substitution. Okay? So u is cotangent. Derivative of cotangent is negative cosecant squared. So you have u squared negative du. Okay? So therefore you're going to get negative u cubed over 3. Okay? So you get minus fraction 64 over 3 cotangent cubed. Okay, so cotangent cubed over here. All right, and here are our limits. Okay, so lower limit of alpha and the upper limit of pi over 2. Just this part, please. Yeah. Okay, there we go. So yeah, you want to pause one more time and plug in the endpoints. All right, so plugging in the endpoints, reminder that alpha is the inverse tangent of 4/3, which means that the tangent of alpha is 4/3, and the cotangent of alpha is 3/4. You have to flip it over. Okay, so we'll need that when we plug in our endpoints. Pi over 2, no problem. Pi over 2, cotangent pi over 2, cotangent cube, pi over 2. But guess what? Cosine over sine pi over 2, the cosine is 0. So these two terms just disappear. Okay, plug in alpha. Minus 625 over 4 alpha, which is tangent inverse 4/3, minus 136 cotangent alpha, and then plus 64 over 3 cotangent cube alpha. Okay, so we need to plug in 3/4 into our expressions here for cotangent alpha. So 136 times 3/4, and then 64 over 3 times 3/4 raised to the power 3. Okay, so this portion we can simplify. What do we got here? That is, let me make a copy over here. It's refusing. There you go. Ooh, that's just negative 93. Okay, so therefore our final answer is just this, minus 93. Okay, I sure hope that's positive. Yeah, the whole thing is positive. Not a very large number, okay, because remember, it's just a little sliver of that parabolic solid. Right, we're going to do one more problem for this video, and this problem will involve one of these special kinds of circles, okay? So hopefully you remember them from pre-calculus. Their polar equations look very simple. It's just r equals some constant times cosine theta, or some constant times sine theta, okay? So here we have a couple of examples. This is what r equals 4 cosine theta looks like. So look at how 4 is on the polar axis. Cosine of 0 is 1, so that r is just equal to 4. Okay. Similarly, here we have r equals 5 sine theta. So notice how it's now oriented symmetric with respect to the y-axis. Okay. So on the y-axis, positive direction, your theta is pi over 2. Sine pi over 2 is 1. That's why we see a 5 over there. Okay, but why should we believe that these are circles? Maybe they're just deformed ellipses of some kind. Okay, so of course, the key to that is your conversion formulas. Okay, so here we did it for the first family. We have a cosine theta for your r. Remember that x is r cosine theta. So therefore, you're missing an r on the right side. So what you do is you multiply both sides by r. You'll get r squared on the left, and on the right, r times a cosine theta. R cosine theta, that's your x. Okay? So you have a left behind. R squared is x squared plus y squared. Okay? So keep this in mind. You're going to see circles with this equation. Okay? And that's going to tell you that this came from this kind of a circle. Okay? But let's keep going. Complete the square. Bring the ax over to the left. So to complete the square, take half a over 2, square it. A squared over 4 added to both sides. Okay? So these three are a perfect square. X minus a over 2 quantity squared plus y squared is a over 2 quantity squared. Okay? So now we are assured that it really is a circle and not just impersonating a circle. So the center is at a over 2, 0. The radius is not quite a over 2. It's the absolute value of a over 2, okay? And that's because we allow a to be positive or negative, okay? As you can imagine, if we had negative 4 cosine theta, the circle will be on the left. And if we had negative 5 sine theta, it will be down here, okay? So we can see that the diameter is the absolute value of the coefficient that we have for cosine or for sine, okay? So of course, if we had a sine theta, the right side will be a times y instead of a times x. Very simple, okay? So what we're going to do is for our final example, we are going to cut our really tall paraboloid with a cylinder, and we'll keep oriented to the y-axis, just like we did with our last example. Oh, one more thing before we go back to scientific notebook. Let's think about the angles, okay? These are general polar regions because, again, stand at the pole, shoot arrows into your domain, okay? So if this were our domain, where do we enter? Oh, we're already there. We enter at r equals 0, and we exit at the circle, 4 cosine theta. Enter at 0, exit at 5 sine theta, okay? What about the angles, though? What is the initial angle and the terminal angle, okay? So for here, it would be convenient to have the initial angle at negative pi over 2 and the terminal angle at positive pi over 2. Okay. Similarly here, initial angle of 0, terminal angle of pi. Okay. So we're going from minus pi over 2 to pi. We're going from 0 to pi. Okay. So that is summarized down here for our domains. Okay. And that might surprise you a little bit, okay, because, wait a minute, that's only pi. Doesn't cosine have period 2 pi? Same for sine. Where's the other pi? Okay, so it turns out that if you go outside of here, you're just going to be retracing your steps, okay? So go beyond pi over 2, you're going to start repeating the circle. We're going to see that in a little bit when we go to GeoGebra. Okay, last problem. We're going to start with the same circular paraboloid, again bounded below by the xy plane, but instead of that y equals 4, we're going to forget about that, and we want to be inside the cylinder x squared plus y squared equals 5y. Okay, so again, this corresponds to, that's the polar circle, that is r equals 5 sine theta. Okay, so we are going to see what this looks like now in GeoGebra. All right, so I want to show you what happens if you try to input our polar curve here, r equals 5 sine theta. So this time you really have to use the Greek letter theta. Otherwise, it won't understand what you're saying, and it would just, actually, it will understand you, misunderstand you rather, as thinking you just want the regular sine wave, okay? But here, notice that we do get the circle, okay? So here's our x-axis, here's our y-axis, but we don't see a cylinder, okay? Think of this as like a little cookie cutter, and then you're going up and down this portion of the solid, okay? So unfortunately, that we can't really appreciate what the solid looks like over there, okay? So I have a little trick to go around that. So let's just hide this. Okay, so you can use the surface command, but it's going to be a little bit smart way to do it, okay? So we're going to kind of sneak around it. Okay, so remember you have to put x, y, z. I'm just using that as a place marker, okay? T will be our theta. Okay, if you're doing it by surface, you don't have to use the Greek letter theta. Okay, so we're going to go from for sine theta, the domain is 0 to pi. Okay, so 0 comma pi. All right, and then I'm going to make z go up and down. Okay, so since we know that the paraboloid stops at 25, let's just go all the way to 25. Okay, so u will go from 0 to 25. Okay, so that will be the z. Okay, z will be u, and z will be going up and down from 0 to 25. Okay, how about x and y? This is where the intelligence comes in. Okay, so you need the conversion formula x equals r cosine theta, y equals r sine theta. Okay, our curve is 5 sine theta. So x is a, delete a, 5 sine t cosine t. Okay, and b will be 5, it's starting to form, sine. Okay, so let me see if it responds to, okay, let's try, okay, there we go, 5 sine, it's not doing it automatically, sine squared t. Okay, there you go. Ooh, okay. So why? Because we have 5 sine t, another sine t, so sine squared t. So there you go. There is your cylinder. Okay, so it really is like a cookie cutter, except notice it's not centered. Okay, so it's getting, let's look for you from the top. Check it out. See, you're getting that circle, but it is centered on the y-axis, not at the origin. Okay, I'm drawing it as a surface, which is why it's not as smooth as it should look when you just do z equals f of x, y, or whatever. Okay, so yeah, zooming out, we can appreciate what the full solid looks like. Ooh, there it is. Okay, so we're only getting this portion of our solid. Okay, ready to set up. So what did we say? Theta is going from 0 to pi. And then our r, starting at the pole, we go from 0 to this circle, r equals 5 sine theta. Okay, it's the same function as before. So we have 25 minus r squared, r dr d theta. Okay, so yeah, again, I invite you to pause the video and see how far you can go. Okay, I'll see you in a little bit. Oops, guess what? I just realized I had an oversight. Remember how we said that you only have to take half and then double? Previous example, there should be a 2 doubling at every step of the way. Okay, so the final answer will be twice this amount. Okay, so we only need pi over here, and we have over 2 over here, and I guess this becomes 186. Okay, so that should be the final answer there. And same thing with what we're doing now, we should double that integral. All right, so this is what I have so far. Same thing as before, 25r minus r cubed, and remember to double this time. So we have same antiderivative, plug in the endpoints, 5 sine theta, that becomes 5 squared sine squared, r to the 4th becomes 5 to the 4th, sine to the 4th, okay? So because of the 2 there, that 2 goes away, and that 4 just becomes 1/2. So notice that you have 25 is 5 to the 2, so that's 5 to the 4th, another 5 to the 4th. So all of those 5 to the 4ths can get out of there. So we have, as before, 625, 5 to the 4th. So this part can go away, and this can go away. And you're probably wondering, okay, I am not too crazy about that sine to the 4th, but we do know what to do with sine squared. Okay, so remember to do your power reduction formula. You do it twice over here. So you plug in your 1 minus cosine 2 theta over 2, and then you have to square it. And you'll need to apply the power reduction formula one more time carefully. Okay, so give it a try. Pause the video. I'll see you in a second. Okay, so a little further. Sine squared is 1 minus cosine 2 theta over 2. Same thing for sine squared here, but you square the whole thing. Okay, so when you do that, you're going to get a 4 in the denominator times another 2. So you get 1/8. Okay, and square the numerator. And then I decided to take the 1/8 outside just because I don't want to deal with fractions as much as possible. So it means I owe a 4 for the first fraction. 4 minus 4 cosine 2 theta. And then I went ahead and squared here. So 1 minus 2 cosine 2 theta plus cosine squared 2 theta. Okay, so as I was saying, you need to do another power reduction here. Okay, but this time instead of just theta, you have 2 theta there. So therefore, you should have 1 plus cosine 4 theta over 2. Okay, so pause one more time, and I'll see you in a little bit. All right, so we're heading for the home stretch. So that's a -1 and a +2, and a minus cosine squared 2 theta. So there's the power reduction. It's 1 plus cosine 4 theta over 2. Okay, and then simplify a little. 4 minus 1 is 3. Minus 4 plus 2 is -2 cosine 2 theta minus that. And I decided to take out the 2, so 8 becomes 16. We get 6 minus 4 cosine 2 theta minus 1 minus cosine 4 theta. Okay, so 6 minus 1, 5. Stay, integrate. 5 theta minus 2 sine 2 theta, a little u sub over there, minus 1/4 sine 4 theta, and we're ready to plug in 0 to pi. 0, everything goes away, yay! But for pi, we get 5 pi there. Sine of 2 pi is 0. Sine of 4 pi is also 0. Yay! So therefore, our v is just this times 5 pi. Okay, so 5 pi over there. That's our final answer. Okay, so of course that's a positive number, but that's 613. I did keep our answer from before. Are you there? Yes, there you are. Okay, so this is the answer. Copy of the answer that we got from our very first problem. Okay, so we had the complete parabolic solid. Okay, and in that one, we didn't do any shortcut about taking half or whatever. We did the complete 0 to 2 pi. Okay, excellent. So there we go. Yeah, this is one of our longer videos. So I hope you enjoyed it. There was quite a bit of integration and geometry and setting up over there. A lot of integrals that you may or may not have forgotten, have remembered, and some identities that will appear in many of these problems. Okay, so don't forget your 1 plus tangent squared is secant squared, 1 plus cotangent squared is cosecant squared, and of course the related antiderivative formulas. Okay, so on that, thank you again for watching, and I'll see you at our next video. Bye!